Okay, good morning everybody, or good afternoon, or good evening, whatever time you're listening to this. This is John here, and I'm going to work on some exam problems from the exams that I gave you. So we'll see how this goes. I have not done these exam problems on my own in a long time, so I'm not entirely sure how this is going to go, but hopefully I can give you some insight into how I would think about a problem and how maybe if I were taking the exam and if I got stumped somewhere, where I would go. So here we go. I'm starting with problem 2 from exam 1 here, and this is kind of a mix of what you've already learned and what you already had in your vector exam and what you're going to have on the next exam. So let's start with the question. So it states a force F equals 10I minus 8J plus 2K kilonewtons, this force right here, and is applied at point C of the pipe assembly shown. So part A is determine the magnitude of the component of the force that is acting in the direction of the pipe segment BC. So we'll think about that one. I'll go ahead and read part B while I'm there. Part B, determine the moment of the force about point A and report your answer in Cartesian form. So this is kind of interesting to think about. We'll start with part A, of course, as you normally would in an exam. I'm not entirely sure what to do here if I'm thinking about it. So we have to read the question over and think about what they're really asking. So determine the magnitude of the component of the force that is acting in the direction of pipe BC. Well, as we can see here, this force is acting off of point C in some direction. We're given the direction, but it's kind of hard to tell. And we're also given pipe BC here. Now, when it asks for the magnitude of the component, I'm assuming that means they want the projection of this force along BC. Now, this is something that would have been in maybe question 2 of your vector exam, the last part where they wanted the projection of the forces along certain segments. So this is kind of what we're doing here. So I also have the equation sheet right next to me, and we can use this equation sheet to kind of guide our way through. And so I'm going to show you right here. So for a line or axis, and there's that. Basically, that's showing that the force parallel to the axis that we want it on, or the force along this line here, for that, we're going to take A dotted with the unit vector of that axis. So basically, we're showing that for the force along B, let me see here. So I'm just going to write projection of F along BC. And this is going to be equal to, we're going to want to first dot the force with the unit vector BC, and then multiply that out by the unit vector BC. Well, actually, my bad. It's asking for magnitude here, which means that we just want the magnitude of the force here. This value here should give us the magnitude, and then by multiplying it by the unit vector, that would turn it into vector format. But we just want the magnitude along it. So we're going to take our dot product there and figure it out. So what we need to know is we already know what F is. F is equal to, I'm going to write in this form, 10, negative 8, and 2. Now we want UBC. So what we need to do first is find the vector of RBC. And from here, we want to take a look at this graph and find that the point of B is 0, 0, 0. It's right here on the origin, so that'd be 0. And then we need the point of C. So if we look at C in the x direction, it looks like it's over 2, or 3 meters. I'm sorry. In the x direction, it'll be over 3 meters. In the y direction, it'll be over 4 meters. And then in the z direction, it'll be negative 1 at C. And so RBC in its format is going to be basically equal to, we can just say C minus B, and I mean that by the points. the point C minus point B. So essentially this is going to be 3, 4, and negative 1. And I'm saying that because we're taking all the points of C and we're subtracting the points of B. However, when B is at the origin, all of its points are 0. So basically, the position vector from B to C is going to be equal to, or have the same points as the points of C. And so that's what we've got for that. Now to find the unit vector, we know that a unit vector has to be the position vector divided by the magnitude. That's what makes it the unit vector, and that's what makes the unit vector just equal to 1. So we're going to find, first of all, we're going to find the magnitude of our BC, and that's going to be equal to, we'll take the square root of 3 squared plus 4 squared plus 1 squared. And when I get my calculator out, I apologize about that. I'm recording in my den, so I had a slight interruption there. But what we were doing was we were calculating the magnitude of the force, or of the position vector from B to C. So we'll just get on our calculators and punch this in. We'll take the square root of 3 squared plus 4 squared plus 1 squared, and I get about 5.09902. It's better while you're doing the problem to use as many sig figs as you can, and then you'll round at the end. Because otherwise, if you start rounding too early, your number will be a bit off at the end. So that's kind of some test advice that you guys might want to know. And so for the unit vector BC, it's going to be equal to, let's see, 1 over 5.09902 times our position vector 3, 4, negative 1. And that's going to be equal to, over here, 3 divided by that, we're going to have a 0.5883i, and then this is kind of my bad, I don't have enough space to write much over here, so I might have to start going below. We're going to essentially do the same thing with the other, so 4 divided by 0.5099 is going to be plus 0.7845j, and then k is going to be negative because that's negative 1, and 1 divided by our magnitude there is going to be 0.1961k. Now one thing to check to make sure that you did do the unit vector right, that I always like to do, is in my calculator I always like to take the square root of all of these combined. So let's take 0.5883 squared plus 0.7845 squared plus 0.1961 squared. And here we get 0.99996 or whatnot. Basically that means 1, and that means that your unit vector does indeed have a magnitude of 1, in that we hopefully did it correctly, or at least it's not way off if we did do it wrong at all. So it's always a good idea during the test to check your work and make sure that what you're doing is correct. That'll eat up some of your time, but it probably would be worth it in the long run. So we've got our unit vector here, and now all we want to do to get the projection of F along BC, or get the magnitude along it, is to dot the force with the unit vector. So we're going to get that. We're going to take our force, which we're given as 10, negative 8, 2, and dot that with our unit vector, 0.5883, 0.7845, and negative 0.1961. And draw a line just to kind of make sure we keep those separate. So we're going to take the dot of these. Hopefully you guys know how to do a dot product, but I'm going to just show all my work here. We're going to take 10 times 0.5883 minus, I'm going to do minus just because this is a negative 8 here, 8 times 0.7845, and then again another minus because got another negative value here, 0.1961. And what we're going to get when we calculate this all out, I can put my calculator on the screen there, times 0.5883 minus 8 times 0.7845 minus 2 times 0.1961. And I get a negative 0.7852 kilonewtons. Now, I'm going to be honest with you. When I see this number, it seems a little bit low to me, just considering how big these numbers are and how low this seems. I'm not entirely sure what happened there, but it's one thing for us to kind of look at. The picture might not be totally the most accurate, but we can kind of base off that. If we look at it, these points here almost look like they're orthogonal or perpendicular to each other. And what we know about dot products is when vectors are perpendicular or orthogonal to each other, their dot product will be 0. Well, since these look like they're almost that way, it kind of makes sense that the magnitude would be close to 0. So the question is asking for the magnitude, and that means that this negative sign here doesn't exactly matter. We just want the value here. So I'm going to go ahead and circle that. And also down below, it'd be a good idea if you put in the force parallel to BC is equal to 0.7852 kilonewtons. And that's just because it asked for the magnitude. So magnitude doesn't really care about whether it's positive or negative, it's just the value itself. Okay, so we've got part A done, hopefully done correctly. And we can move on to our part B. So determine the moment of the force about point A. Report your answer in Cartesian form. So the moment of the force, this is going to be a cross product. If we take a look at our equation sheet right here, we should have an equation down here. Moment of a force about point O. And we're going to want to use this equation here because we're given the force in a vector and the distance is going to be in a vector. And so we're going to have the moment in a vector as well. And it's asking for it in Cartesian form, which means that we want the moment in vector format, which means either the I, J, K, or this little triangular bracket thing that I've used earlier. So if we want to go ahead and do that, it always helps. Another exam tip is to always write out the equations that you want, that you're going to use. So it's going to be the moment at A is going to be equal to the position vector, and the position vector is going to be AC crossed with the force vector. So let's take a look at this. We need our vector of AC. Let's go back up to our picture and see where we have point A is at. So point A in the x direction is 0. In the y direction, it's actually going to be negative 2. And then in the z direction, we have another 0. So we can use that to find what our position vector AC is. So RAC is going to be equal to, essentially it's going to be C minus A, and that's going to be equal to 3 minus 0, 4 minus negative 2, and negative 1 minus 0. And that's just me showing the points here. So for x in the z, or in the c, at point C I mean, is going to be 3, and the x at point A is 0, so 3 minus 0, and then just go on through with that. And we do that, we're going to get our vector in 3, 4 minus negative 2 is going to be 6, and negative 1. So that's what we've got for a position vector. Again, force is given to us as 10, -8, 2. And now we want to cross them. So one important thing to know when you cross product is you always want to make sure you put the position vector first, because otherwise you're going to get a negative value and it's not going to be correct. So you always want to make sure you have your position vector first. And so we've got MA is going to be equal to, here we have our vector, I, J, or not our vector, I'm sorry, our matrix here. So we have our I, J, K in here, and then our position vector is going to be 3, 6, -1, and then down here we've got 10, -8, and 2. And so let's calculate our cross product. What I always like to do with cross products is I like to say I want to find what I is, I want to cover up I and go through with everything else and find out how to do it. So we would first take 6 times 2, and then we subtract -1 times -8 from that. I'll show you over here in writing. So if we want to find the cross product at I, we're going to take 6 times 2 minus -1 times -8. We've got that in our I. And now we want to cover up J. Now one important fact is if we do it in my method where we cover up J and then cross this way minus that way, we're always going to want to put a negative sign in the middle. There's other methods to do this that don't require you to do the negative sign, but the way that I'm showing you here, make sure that you'll put the negative sign right here, because otherwise it'll be the wrong J, or the wrong direction in J. So we're going to want to take 3 times 2, 2 minus, we're going to have a -1 times 10. We've got that in the J. And again, I've ran out of space. We'll go ahead and do K. And K can go back to being positive here. So we're going to take 3 times -8 minus 6 times 10. And that's going to be in our K. Now if you go ahead and calculate this all out, let's see, 6 times 2 is going to be 12. And then we're going to be subtracting -1 times -8 is going to be +8. So 12 minus +8 is going to be 4i. And then we go over here in the J. We're going to have 3 times 2 is going to be 6. And then -1 times 10 is going to be -10. And so 6 minus -10, we're going to have 16. So that was 6 minus -10 is 16. We got this negative sign out here, so it's going to be -16 in the J. And then lastly, in our K, we're going to have 3 times -8, which if I remember correctly, that should be a -24. And then we're going to have a 6 times 10, which is going to be 60. So -24 minus 60 is going to be -84K. And that should be our moment right there. Now, I did these all in my head. It might help if you did it by hand just to check, or by calculator, my bad. Did it through your calculator just to check and make sure that you get the correct values, but here's what I've got here. And so if we write down in our answer key, you've got the moment about A caused by this force here is going to be 4i minus 16j is 84k. And this is how I did problem 2 from exam 1. And I hope you guys found this helpful. I hope the answer made sense to you guys. If not, feel free to email me or call me or text me or whatever. And hopefully we can get it all correct, and hopefully you guys can study well for your exam. So thanks for watching, and I hope you guys watch the other videos, and I hope you guys have good luck studying. Thanks. One quick little note about this problem here that I forgot to mention when I was first doing it is we always want to put units on everything. So I put units here on the projection of F along BC like I did earlier, but now we want to make sure we've got units for this moment here. And so if we look at it, the force is given in kilonewtons and the distances are in meters. And so the force down here is going to be kilonewton meters. And always want to make sure you put your units on there.